From your past chemistry class, you may remember that there are 7 strong acids. These are ones that you will need to memorize because once you know these acids, everything else you'll know are weak. So they are the halides, the hydrogen halides, except for hydrofluoric acid. So starting with hydrochloric acid, hydrobromic acid, and hydroiodic acid, as well as these polyatomics, so nitric acid, sulfuric acid, and then chloric acid and perchloric acid. So just remember the halides, and then nitric, sulfuric, and then chloric and perchloric. So these happen to be strong electrolytes, so they completely dissociate in water. So that means that if we have one of these strong acids, we'll just call it HA to be general, dissolving in water, they go only in the forward direction to form hydronium and the conjugate base, which means that there will be no acid left in solution. It will be completely dissociated. So for these acids, that means that the concentration of hydronium or hydrogen ion in solution is whatever the concentration of the acid that you put in is. I also do want to make a note that for sulfuric acid, not both of the hydrogens come off as strong acids, but just the first one. So all of these release one hydrogen ion. So strong bases are all of the soluble hydroxides, so OH negatives, which include all the alkali metals, and the heavier alkaline earth, so calcium, strontium, and barium, but their solubilities are a little bit lower. So these again will dissociate completely in water. So we have our metal hydroxides that are aqueous. That means that we have the metal ion that's aqueous completely dissociating into that, plus our hydroxide ion. Or we could have our metal, if it's an alkaline earth, it would have 2 hydroxides since its charge is plus 2, which would go to our metal 2 plus and 2 hydroxides, which are aqueous. So the big takeaway here are that the arrows are only one direction. We are not in equilibrium here. We don't have a reverse reaction happening. So let's calculate the pH of perchloric acid when it's 0.04 molar. So we know that this is a strong acid, so the concentration of the acid here is the concentration of hydrogen ions. So to find the pH, we'll go pH is negative log of hydrogen concentration. So we'll do negative log of 0.040, and that will give us 1.40. In this other example, we have a solution of nitric acid, so we identify that as strong, and that has a pH of 0.34. So finding the concentration, so again we know pH is negative log, so if we want to find the hydrogen concentration, we need to do the opposite. So we need to say hydrogen concentration equals 10 to the negative pH, and so that will be 10 to the negative 2.34, which gives us 4.57 times 10 to the negative 3 molar. Once again, we can do something similar for our bases here. So we want to know the pH. So we can either find the hydroxide concentration. So since it's a strong base, we know that the hydroxide concentration is the same as the sodium hydroxide. So our OH concentration is 0.028 molar. So if we want to find, we could do POH, or let's just find the hydrogen concentration here using our kW. So 1 times 10 to the negative 14 equals hydrogen times hydroxide. So we'll divide by the hydroxide concentration, which is, so I'm going to just erase that. That was just to fill it in so you remember. And so that's 0.028 molar, giving us a concentration of hydrogen being 3.57 times 10 to the negative 13 molar. That's for hydrogen, so we could take the negative log of this whole thing to get pH, and that will give us 12.45. So let's just think about what that means. That's very basic. Well, we have a high concentration of hydroxide here, so that makes sense. When we have our concentration of calcium hydroxide, so we have 0.0011 molar of calcium hydroxide. So we need to take into account that for every 1 mole of calcium hydroxide, we have 2 moles of hydroxide. So our concentration of hydroxide is going to be 0.0022 molar. So because we have 2 of them, so the concentration is going to double. So keep that in mind. So we could do this a similar thing and find that the hydrogen concentration is the kW divided by this hydroxide concentration, which equals 4.55 times 10 to the negative 12 molar, and take the negative log of that, and that will give us 11.34 is the pH of that solution. So again, we have a high concentration of hydroxide, so a high pH makes sense. Now when we get into weak acids, we kind of have a more complicated situation. When a weak acid here, we'll call it HA again, dissociate, or it gets dissolved in water, some of it will dissociate into hydronium, but some, and also the conjugate base, but there's going to be, because it's only some of it, so some of them will go back. So we are in equilibrium, so that's where we really have to pay attention to these arrows here. Since we are in equilibrium, we're going to have a equilibrium constant. We'll just call it K for a sec. That K is equal to, so we're going to use our equation. So we have hydrogen concentration times the conjugate base divided by HA, our acid, and then we could divide by water, but it's a pure substance, so it's just 1. Because this is for every acid, we call this equilibrium constant Ka for acid dissociation. So when K is large, that means that we have a stronger acid because we're having more. So let's just think about that for a sec. So big K means more products. So the larger that Ka means we have dissociated higher. So if we remember that little acid chart where we had strength of acids and then strength of base going down. So if we have a bigger Ka, it would be higher up on this chart, and a lower Ka would be below. So we could also say strength of acids we could rank here, but also we could rank it increasing Ka. So when we compare strong and weak acids, strong acids completely dissociate. There's no reverse direction. And weak acids only partially dissociate. So we can see here a strong acid, we don't see any HA in here at all. We have only conjugate base and hydronium, but with a weak acid, we're still going to have some of our original acid left in solution, and only a small amount of conjugate base and hydronium. Here are just some formulas of Ka values for different acids. So we could see chlorous acid is pretty similar to like chloric acid. It's not a strong acid, but it does have a larger Ka than some of the other ones. Hydrofluoric is one of those that didn't get included in the strong acids, mostly because fluoride is so small that hydrogen it is pulled so tightly it doesn't want to give it away. So it's also a stronger weak acid than some others. We could say they go all the way down to something like phenol. We wouldn't even consider that really an acid. It really doesn't want to let go of that hydrogen, so its dissociation constant is very small, even smaller than, you know, the water dissociation, so just water auto-ionizing. The first thing we're going to be able to do is learn how to calculate the Ka constant from the pH. So in this example, we have a pH of a 0.1 molar solution of formic acid, so we can identify that as weak, at 25 degrees Celsius is 2.38. So there's the pH. So calculate Ka of this acid. So first thing we know about Ka is the expression. So that will be for this reaction hydrogen. It's called hydrogen plus the conjugate base, and divided by the original acid, formic acid. So to be able to calculate this, we need to know the equilibrium concentrations. So from the pH, we can know the hydronium concentration, and that will be the same as the conjugate base because they're going to dissociate at the same rate since it's a the coefficients are 1-to-1. So we know that the hydrogen concentration is equal to the formate concentration, which is, we have the pH, so we need to do the inverse, so we're going to do 10 to the negative pH, so 10 to the negative 2.38 will give us a concentration of these two as being 4.2 times 10 to the negative 3. So the next steps are going to be to set up our ice table for these concentrations, knowing that we know the original concentration because we added it or created this concentration, and then using pH we found the equilibrium concentrations for those, so we can calculate our equilibrium concentration of formic acid. So here's our equilibrium table. We know that we started out with none of our products, and we found, using the pH, the equilibrium concentrations of these two, so we know the change. So that's where you're going to be plugging in. Then we know that both of those went up by that amount, so this, the formic acid, has to go down by that amount. We also knew the initial concentration, so we're going to do that math here. 0.1 minus 4.2 times 10 to the negative 3, and we can get that it's actually pretty close to that same 0.1. So what we get is 0.0958. So what you want to do, actually, a really cool little trick, is we're going to take our change here and divide it by our original concentration. So let's do that. 4.2 times 10 to the negative third divided by 0.1. If that gives you something that's less than 5%, so if you get a number when you do this and it is less than 0.05, then we can actually make an approximation that says that that change is so small that we're just going to use our initial concentration. So what we actually are able to do, when I plug that in, I get that my number is 0.042, so that is less than 5%, and so I don't actually need to use this accurate number. I could use the approximation. So Ka is 4.2 times 10 to the negative third for both hydrogen and formate, so I can square that, and then divide it by 0.1. You need to be able to make those approximations first before you can put it in to the solution. So I'm going to do that, and I'm going to get Ka equals 1.8 times 10 to the negative 4. Now, to prove that is still an okay thing to do, I'm going to just, while you're here, plug it into the calculator, and we can see that if I were to plug in this number instead, then I would still get 1.8 times 10 to the negative 4, so that approximation works. The next thing that we're going to learn about is percent ionization. So percent ionization is just like it sounds. How much of the original acid formed into an ion. So we can find that by saying, well, if it's an ion, well then it formed either hydrogen concentration or formate, in this case, or a conjugate base. So it'll just be easier to say whatever concentration of hydrogen we have at equilibrium divided by original acid initial times by 100. So in this example, we had our hydrogen concentration and our initial formate. So for the percent ionization of this compound, we'll do 4.2 times 10 to the negative third divided by 0.1 times 100. And so we can see that this ion ionized 4.2%, which is actually what I did originally to do that approximation. So when it ionizes greater than 5%, we can't make that approximation that the change in concentration is so small that we can use our initial concentration. We won't be able to do that if percent ionization is above 5%. FYI, I realized that this problem is exactly the same as the other one, so I'm changing it. So assume now that a student prepares a 5.5 times 10 to the negative 3 molar solution of fluoroacetic acid, and we're just going to call that acid AJ. It's not the formic. And the pH is found to be 5.27. So from that, we're going to calculate the Ka for fluoroacetic acid. So we're going to use a general formula where HA goes to I want to do hydrogen, doesn't really matter, plus the conjugate base. So, and in our ICE table, from this information, we can know the initial concentration, because it's given, of all the things. And then we also can use the pH to find the equilibrium concentrations of our products here. So we're going to just plug in 5.5 times 10 to the negative third molar for our acid, and then we're going to use the pH. We want to find the hydrogen concentration, and that is 10 to the negative pH. So we're going to do 10 to the negative 2.57 is 2.69 times 10 to the negative 3 molar. So plug that in here for both of them. And now I know that. So we know that we started off with 0 amounts of our products. That will be the case for all of these. So those all went up by 2.69 times 10 to the negative 3. And before we can make our approximation to see if the change is so small that we can just use our initial acid concentration, we need to do percent ionization. So this is a question in the future slide that we're actually not even going to do on the future slide. We're just going to do it here to know if we can make that approximation. So we're going to do our concentration of hydrogen, which is at 2.69 times 10 to the negative 3, divided by our initial acid concentration, 5.5 times 10 to the negative 3, and times 100. So when we do this, we see that we get 48%. So almost half of this acid broke apart and formed ions. So we cannot make that approximation. So we do need to do the change. So we're just going to go down by 2.69 times 10 to the negative third. So do 5.5 times 10 to the negative third minus our change. And we get 2.81 times 10 to the negative third. Plug all of this into our Ka expression. So we get our hydrogen concentration times our conjugate base concentration, which are the same. So square those. Divide by our equilibrium acid concentration, which in this case is 2.81 times 10 to the negative third. And you should get 2.5 times 10 to the negative third. So we can see that this is a stronger acid than our one from our example with formic acid. Moving on, we want to do a similar thing for niacin. So we have a molecule here. Niacin is a B vitamin that is an acid, has a little acid region here. So we're going to call this HA again. And we make a 0.02 molar solution of niacin, and its pH is 3.26. So we're going to write our equation. HA goes to H plus our base. We're going to set up our ice table. So initially we have a 0.02 molar, no concentration of our ions. And we can use our pH to find acid concentration or hydrogen concentration, 10 to the negative 3.26 or pH. And we find that our hydrogen concentration and acid conjugate base is 5.50 times 10 to the negative 4. So before we even continue on to do our change, actually let me plug those in here into our ice table. We're going to do our percent ionization. So we'll do 5.50 times 10 to the negative 4 divided by 0.02 times 100. And we get 2.7%. So that is small enough that we don't actually need to do any math here, and we can just make the assumption that the equilibrium concentration is the same as our initial concentration. So now when we plug in Ka here, we're going to do our 5.50 times 10 to the negative 4. We're going to square it and divide by our equilibrium, i.e. our initial concentration. And we get our Ka, that's equal to 1.51 times 10 to the negative fifth. So this is actually a weaker acid than the formic acid and our fluoroacetic acid. And we actually already calculated our percent ionization on the previous problem, so I'm going to skip this slide. Now we're going to calculate the pH using Ka, where we just learned the opposite. So the first two steps are very familiar. We're going to write the chemical equation for our acid dissociating. You can choose to write the water in the equation if you want to visually picture the water grabbing the hydrogen ion, but you don't have to. Then you're going to write up the equilibrium constant expression, so Ka. Then you're going to set up an ice table so we can find out their equilibrium concentrations, and we're going to use X again. Then we can plug those into our equilibrium expression and solve for X, since we already know Ka. And if we can, we're going to really try to make assumptions so we don't have to do as much quadratic formula. So in this example, we're going to calculate the pH of a 0.3 molar solution of acetic acid. So the formula is already written out. So we're going to write the Ka expression for this, which is H3O plus, and then here's acetate, and then divided by acetic acid. So let's set up an ice table now. So we're going to have our HA goes to A plus hydrogen. So we have a 0.3 molar solution of our acetic acid, so that's what we're starting with. And we don't have any of our ions, so those are going to be the same kind of thing. Now, we don't know how much it changed by, so we're going to write minus x plus x plus x. So we have 0.30, I'm not going to write molar, and then write minus x, and then x and x. So if we plug this into our Ka expression, we have x squared over 0.3 minus x. So here you see that we have that already set up. So we are going to want to look up the Ka value. Now if the K is pretty small, like we're talking significantly smaller than our initial concentration, then we can make the assumption that x is negligible for our subtraction here. So if we assume x is way smaller than 0.3 molar here, then this subtraction turns into just 0.03 molar at equilibrium. And that makes it way easier because we don't actually have to do quadratic formula. So what our equation turns into is Ka, which in this case for acetic acid, we could look at a table, is 1.8 times 10 to the negative 5th. That equals x squared divided by 0.30. So then we can multiply by 0.3 and then square root, and what we get is that x is 2.3 times 10 to the negative 3rd. You can then, now we know hydrogen concentration, so you can see if it's pretty small. So we could do 2.3, basically we're calculating percent ionization, 2.3 times 10 to the negative 3rd divided by 0.3, and that is 0.7 or 0.8%, so it's very, very small. So basically if you're looking at the Ka and it's like 10 to the negative 4, 10 to the negative 5, or even smaller, then you're dealing with a pretty weak acid, and this subtraction is going to be negligible. So in this case, our X, which is our hydrogen concentration, we know it now, so we can find the pH, which is our ultimate goal here, by taking the negative log of 2.3 times 10 to the negative 3rd, and we get a 2.64 pH. So now let's calculate the pH of a 0.2 molar concentration of hydrocyanic acid. So we're going to use our weak acid table, which we have in our notes, and we can see hydrocyanic acid is very, very weak. It's one of the weaker ones on this table. So that's a good hint that that approximation is going to come in handy. If we're looking at something like chlorous acid, then we probably wouldn't be able to make that approximation, and we would need to do the quadratic formula. So we're going to first write out our equation, and I'm going to write it down here so we can do our ice table under it. So that goes to hydrogen and cyanide, and we're starting out with 0.2 molar there, none of those, and then we're going to have our change subtract x at x, so 0.2 minus x, and then x. So we're going to have our Ka, let's do our equilibrium expression, it's going to be our acid, or our hydrogen, and then our cyanide, divided by hydrocyanic acid. So that ends up, and this whole thing equals 4.9 times 10 to the negative 10. So let's plug that in. 4.9 times 10 to the negative 10 equals x squared over 0.2 minus x. So if you would like to, you can do quadratic formula, but we can look at this K value here, our acid constant, and know that it is so small that we don't actually need to make that approximation. So bringing this down, we can solve this. So we're going to just get rid of our minus x here. Come on. Maybe. There we go. And we're going to just solve for x by bringing up 0.2. And when we do that, we get 0.98 times 10 to the negative 10 equals x squared. So we're going to square root the whole thing. And we get the hydrogen concentration, which is x, equals 9.9 times 10 to the negative 6 molar. So if we want to find pH, we're going to take the negative log of that. When we take the negative log of 9.9 times 10 to the negative 6, we get 5.0. Let's do one more practice problem before we move on. We're going to calculate the pH and percent of hydrofluoric acid that's ionized. So we have our situation set up here, very nice. And what we're going to do is solve for this. So if we look at our table, we know that Ka for hydrofluoric acid is 6.8 times 10 to the negative 4. So that's going to be our hydrogen concentration plus our fluoride times our fluoride concentration divided by the acid. And so when we plug that in, if we make our approximation, we're gonna get x squared over 0.1. So if we solve for this, we multiply by 0.1 and then square root it, so we get 6.8 times 10 to the negative 4. Negative 4 equals x, that should be negative 5 now, equals x squared. We square root the whole thing. We get that our x, or hydrogen concentration, is 8.2 times 10 to the negative 3rd molar. So what we want to do is calculate percent ionization to see if this is a good enough approximation. So if I do our percent ionization to be 8.2 times 10 to the negative 3rd divided by 0.1 times 100, I get 8.2%. Well, that is bigger than 5, so I cannot use that approximation. So switch colors, and we're going to have to do the old-fashioned quadratic formula. So we're going to now set up 6.8 times 10 to the negative 4 equals x squared times, or divided by 0.1 minus x. So we're going to actually use that situation. So plug in, and we will, so we'll bring this denominator up, and we'll get 6.8 times 10 to the negative 5 minus 6.8 times 10 to the negative 4x equals x squared. The nice part is we don't have any other x squared, so we can just move all of those over. So we're going to get x squared plus 6.8 times 10 to the negative 4x minus 6.8 times 10 to the negative 5 equals 0. Plug that into your calculator, and you're going to get that x, which isn't really that bad, it's just extra steps. X, which is our hydrogen and our fluoride concentration, is 7.9 times 10 to the negative 3rd molar, we can now calculate, just to make sure, that 7.9 times 10 to the negative third divided by 0.1 is still above 5%. So that is now our new percent ionization is really 7.9%. We're going to do the same calculation, but plug in our new number for our hydrogen concentration. So if we take the negative log of this value to get our pH, then our pH is 2.10. One last way to think about strong versus weak acids is to compare what's going on as far as their, one, how they conduct electricity, and also their rates of chemical reactions. So we know that in our strong acids, the hydrogen concentration at equilibrium is equal to our initial acid concentration. So we see here, hydrochloric acid, 1 molar of that does form 1 molar of hydrogen ions. Where our weak acids, our hydrogen concentration at equilibrium is much less generally than our initial acid concentration. So if we look at acetic acid, even though we make a 1 molar solution of acetic acid, we only make a 4 times 10 to the negative third molar of acid, or of hydrogen ions, so it's quite a bit less. So when we look at this example of our acid dissolving a metal, we see that our weak acid, or acetic acid, it's taking a really long time to break down that metal and to react. While our strong acid starts to bubble, it's very vigorous, and the reaction is complete much quicker. So in this one, it's complete already, where in our weak acid, it's still reacting, and then eventually it'll go to completion. So it doesn't affect the final equilibrium of that reaction, but it does take a lot longer to get there. And then lastly, as far as weak acids go, we're going to talk about polyprotic acid. So those ones mean many protons. So we're talking about sulfuric acid or phosphoric acid. Actually, there's a whole list right here. Obviously, you can see ascorbic acid, which is vitamin C. And so they have more than one acidic proton. But it's always easier to remove the very first proton. Every proton is going to actually have its own Ka values. So you'll see the first Ka is always generally quite a bit larger than the next proton to come off, usually by a factor of 3 or greater. So our pH is generally only depending on our first association, because that second amount, the second hydrogen to come off, gives off such a small amount that it really doesn't even impact the pH. In this example, we have carbon dioxide being dissolved in water at 1 atmosphere produces a concentration of 0.0037 molar. So we can kind of think about that with the solubility of gases. A throwback. And so we can assume that all of the dissolved CO2 forms carbonic acid. So this is our reaction. And so we want to know what the pH of our 0.0037 molar solution of carbonic acid is. So we can keep in mind that carbonic acid has 2 Ka values, and we need to compare them. So the first Ka for carbonic acid, so we'll call it Ka1, is 4.3 times 10 to the negative 7. The second one, Ka2, is 5.6 times 10 to the negative 11. So they differ by basically 10,000, which is a lot. So if we want to know what the pH of the solution is, we're going to do a very similar thing, but we're going to only use our first Ka here when we're plugging into our ice table. So let's set it up. We have our H2 carbonic acid dissociates into 1 hydrogen and hydrogen carbonate or bicarbonate. So that's our dissociation. This is what the K's mean. This is our equilibrium for a different reaction, but when we're thinking about forming an acid, we're using this equation here. So we're going to use our ice table. We know from our equation that we have a initial concentration of 3.7 times 10 to the negative third molar of carbonic acid, and at first that doesn't have any dissociation. Initially, it's going to increase those concentrations by x and decrease that by x. So now if we look at this value, the first Ka is 4.3 times 10 to the negative 7. That is really, really small. A factor of 4 times smaller than our initial concentration of carbonic acid. So this would be a good case where we can make that approximation that x is so small that it's less than 5%. You could always check and do a quadratic formula if you'd like, but I don't think that's necessary. So the key thing is we're going to use the first Ka value, so we're going to set 4.37 times 10 to the negative 7 equals x squared divided by 0.0037. When we solve for this, we're going to move that denominator up, multiply it by both sides, and then square root the whole thing. And we're going to get that x, which is equal to our hydrogen concentration, is 4.0 times 10 to the negative 5th molar. So if we want to do the pH, we're going to do the negative log of hydrogen concentration, which will give us 4.40. And we can calculate the percent dissociation by doing this hydrogen concentration divided by our initial concentration, and what you'll see is that it's about 1% dissociated, so that would be a good call to use that approximation. That's all for weak acids. I know it's a lot, that's why we took 2 days to do it, but it's basically the same as our ice tables from before, where we either use x to find our concentrations at equilibrium, therefore pH, or we could use pH and initial conditions to find that change. So hopefully that was not too much for you, and we actually have some nice approximations, so we don't have to do as much quadratics as we did last chapter. Next thing we're going to do is move on to weak bases.